Hello everyone, I'm Zihan from ICT CAS, and I am the final year PhD student. Today, my topic is HPC AI 500, the methodology, tool, and metrics for benchmarking HPC AI systems. First, I will introduce the challenges of HPC AI benchmarking, then the methodology, metrics, and the specification, and finally, the case study and ranking. The first challenge is how to achieve both representative and simple, which essential properties the past successful benchmark practice establish. On the one hand, the spec series such as spec CPU and PARSIC and TBC benchmarks like TBC DS emphasize the paramount importance of the benchmarks being representative and diverse, as no single benchmark or metric measures the performance of computer system on all applications. On the other hand, Top 500 establishes the de facto supercomputer benchmark standard in terms of simplicity. Simplicity has three implications. First, the benchmark is easy to port to a new system or architecture. Second, the benchmarking cost is affordable for measuring system at scale. Third, the number of the metric is not only linear, but also easily understandable. But in the HPC AI domain, massive AI tasks and different metrics with different performance metrics, for example, by far, the most comprehensive and representative AI benchmark suite, AI Bench, contains 17 AI tasks. It's not affordable to implement so many massive benchmarks and further perform benchmarking at scale. Here is an example. This example shows the relation between AI and LU decomposition. The micro benchmark HPL AI evaluates the performance of the HPC AI systems based on mixed precision LU decomposition. However, our evaluation results show a low percentage of LU decomposition in 17 workloads of AI Bench. These results also implies that it is difficult to have both representativeness and simplicity. Although HPL is easy to test, its core workload LU decomposition cannot cover the characteristics of AI workload and cannot provide the information of model quality. The second challenge is how to achieve repeatability. The benchmark maintains being repeatable while AI's nature is stochastic, allowing multiple different but equally valid solutions. Previous work, such as MLPerf, manifests AI's uncertainty by run-to-run variation in terms of epochs quality and the effect of scaling training on time quality. For example, random seeds affect model initialization, data traversal order, etc., and the non-idempotence of floating point operations. AI frameworks use different implementations of operators such as convolution, multiple hyperparameters such as batch size, landing rate, and weight decay. And these four perspectives are all the source to the AI randomness. Here is an example for the randomness of AI. This is the image to test, which is a workload in AI Bench, varies significantly in terms of epoch to quality under different random seeds. The challenge 3 is the inadequacy of micro benchmarks. The first limitation is no information of model quality can be provided. Second, the performance of the operator is determined by the input size. Taking convolution as an example, there are not only batch size channels, height and weight of the input image, but also hyperparameters related to the convolution, such as the convolution step. The huge input space of the operator makes the benchmarking cost prohibitively. Third, an AI workload usually consists of thousands of operators with dependency. A single kernel such as LU decomposition cannot reflect overall performance. Finally, some optimization on the kernel improves flops, but that deteriorate model quality. Example 3 shows the mixed precision, which is a common optimization. Indeed, improves the flops, but reduce the model quality, especially when the scale of the system under test becomes larger. As shown in the figure in the left, the model quality of 8 nodes has reduced 1.4%. Next, I will introduce the methodology of HPC AI500. I will first introduce the workload construction. As I mentioned challenges before, the chosen workload should be representative, repeatable, and simple. Moreover, we also consider the additional requirements in the HPC field. We choose AI bench training, by far the most comprehensive benchmarks as a starting point for the design and the implementation of HPC AI500 benchmarks. We achieve the representativeness from microarchitecture dependent and microarchitecture independent perspectives. From the microarchitecture dependent perspective, we choose 5 microarchitectural metrics to profile the computation and memory access patterns of AI bench training, including achieved occupancy, IPC efficiency, GLD efficiency, and so on. And GPU architecture contains multiple streaming multiprocessors. Each streaming multiprocessors has a certain number of CUDA cores, registers, caches, and etc. Achieved occupancy represents the ratio of the average active warps per active circle to the maximum number of warps provided by a multiprocessor. IPC efficiency indicates the ratio of the executed instructions per cycle to the theoretical number. GLD efficiency and GST efficiency represent the ratio of requested global memory load store throughput to required global memory load store throughput, respectively. We profile the 5 metrics and perform k-means clustering on all 17 benchmarks in AI bench training to explore their similarities through our experiments. Note that we further use the TSNE is a visualization techniques and can reduce the dimension to a low dimensional space for visualization. This figure shows we can find that these 17 benchmarks in the figure are clustered into 3 classes. From the microarchitecture independent perspective, we analyze the algorithm behaviors, including model parameter size and conversion rate, and the system level behaviors, including computational cost, and such as flops for all 17 workloads in AI bench training. Further, we conduct a clustering analysis using this microarchitecture independent performance data, as shown in the figure. Combining these 2 figures, we conclude that the AI bench training workloads consistently cluster into 3 classes using both microarchitecture dependent and microarchitecture independent approaches. Next, I will introduce how to achieve repeatability. Repeatability refers to the variation in repeated measurements, different runs instead of different epochs, using the same benchmark implementation under the identical configurations made on the same system under test. A good benchmark must be repeatable. Thus, repeatability is another critical condition to select workloads for the HPC AI500 benchmarks. However, AI's nature is stochastic due to the random seed and the random data travel, and etc. is hard to avoid. Thus, most AI benchmarks exhibit round-to-round variation, even using the same benchmark implementation on the same system. Therefore, we need to ensure repeatability by choosing relatively stable workloads in various AI tasks. We perform repeatability analysis using all workloads of AI bench training. To eliminate the influence of randomness as much as possible, we fix the hyperparameters for each benchmark. For example, batch size, landing rate, optimizer, and repeat at least 4 times for each benchmark to measure the round-to-round variation. Note that our evaluation uses the random seed and doesn't fix the initial seeds except speech recognition. We use a coefficient of variation, the standard deviation ratio to the mean of the training epochs to achieve a target quality to represent the round-to-round variation. This table presents the round-to-round variation of 17 workloads of AI bench. As we see, each AI benchmark varies widely in terms of the round-to-round variation. According to this table, the most random workloads are video prediction, text summarization, and image to text, and their variation reach 38.46%. And 24.72% and 3.52% respectively for speech recognition. Even sharing the same initial seed, the round-to-round variation still gets 12.08%. In contrast, object detection, image classification, and learning to rank are the 3 most repeatable workloads, and the variation is 1.12% and 1.9% respectively. These 3 workloads, the highlighted one, are consistently classified into 3 classes based on both the microarchitecture dependent and microarchitecture independent approaches. Overall, image classification, learning to rank, and object detection achieve both representativeness and repeatability. Next is we should keep the benchmark simple. Simplicity is another important selection condition for benchmarking. However, benchmarking an entire training session of all 17 workloads in AI bench training is extremely expensive, which reaches up to 10 days. We emphasize that image classification, object detection, and learning to rank achieve not only representativeness and repeatability, but also simplicity. Next is the requirements in the HPC field. First is the dataset. Against other domain AI benchmarks, there are 2 unique differences in HPC AI benchmarking. First, the challenges of HPC AI benchmarking inherent from the complexity of benchmarking scalable hardware and software system at scale. For example, tens of thousands of nodes, significantly different from that of IoT or data center. On this point, we need to make the benchmark as simple as possible, which we have discussed in detail before. The shape of scientific data. Second is the data set. The shape of scientific data can be 2D images or higher dimensions structures with hundreds of channels, while the popular commercial image data like ImageNet often consists of only RGB. Based on the existing analysis, we can conclude that image classification and object detection are the final, and the landing rank are the final candidates to construct the HPC AI benchmark. We investigate the broad application of image classification and object detection in both HPC and commercial field. We choose the most representative workloads and data sets from these two fields. First is extreme weather analysis. Pioneering, for short, is EWA. EWA is a pioneering work that uses deep learning to tackle the classical HPC problem, and it won the Golden Bear Prize in SC18, and it's essentially object detection task, and his goal is to detect different weather patterns in one climate image. Two is the second workload is image classification. Image classification is a de facto HPC AI benchmark used in many state-of-the-art optimization works. Next, I will introduce the hierarchical benchmarking methodology in HPC AI500. First, I will introduce why we need this benchmarking methodology. It's non-trivial to prove the equivalence of two AI benchmark implementations on different systems or even the same system with different skills. Equivalence quantifies how equivalent two benchmarks implementations on different systems or the same system with different skills. There are complex interactions among hardware and software systems, which is further aggravated by the AI algorithm. Even for the same AI algorithms, there are huge parameters significantly impacting learning dynamics, as shown in this figure. ImageNet ResNet 550 training is one well-known showcase for optimizing HPC AI systems. It reports the performance in terms of a ternary tuple, achieved quality flops, and time to quality. The past witnessed the system performance varying widely from 74.6%, 1.6, and 28 to 75.1%, 36.8, and 1.2. And this table summarizes the state of the art and the state of the practice optimizations mentioned in the last slides in ImageNet ResNet 50 training. Unfortunately, without equivalent benchmarking rules stated, we cannot objectively derive the performance edge of one system against the others as an influence of the algorithm level. Motivated by this, we propose a hierarchical benchmarking methodology as shown in the figure. We abstract the system on the test into 9 independent layers and put each layer on the test while keeping the other layers intact, unless otherwise stated. Layer 1 is hardware, including CPUs and networks. Layer 2 and 3 are the related systems, including the operating system and the communication libraries. Layer 4 includes the AI accelerators, such as GPU, and interconnections, such as NVLink, and the libraries, such as CUDA. Layer 5 refers to the AI frameworks, such as TensorFlow and PyTorch. Layer 6 refers to programming model, including parallel mode, such as data parallelism and model parallelism, or pipeline parallelism. And it also refers to the training mode, such as synchronized or asynchronized. Layer 7 refers to the workloads used in HPC AI 500 benchmark. Layer 8 refers to hyperparameters, policies, or settings. Layer 9 refers to problem domain, including dataset, target quality, and epochs. Second, for the sake of simplicity, we propose 3 high levels of benchmarking and put several related layers together on the test. First is the hardware level benchmarking. The purpose of hardware level benchmarking is to evaluate the performance of the hardware of HPC AI system and its associated library. And the users are allowed to make changes in layer 1 and 4, such as changing accelerators or using more efficient communication library. And users also can adjust the learning rate and batch size setting to fit the system skill. And last, users are allowed to change the parallel mode, such as model parallel, data parallel, or pipeline parallel. Second is the system level benchmarking. The proposal of system level benchmarking is to evaluate the performance of hardware, associated library, and AI framework. The users are allowed to change in layer 1 to 5. Compared to hardware level, users are allowed to change or customize the AI framework that used to implement the workloads of HPC AI500. Finally is the free level benchmarking. The purpose is facilitate hardware and software co-design. Users are allowed to change anything, include model and optimizers, and do any optimizations in layer 1 to 8. Next, I will introduce our metrics. We propose valid flops, in short, VFLOPS, to quantify the valid performance that considers both the system throughput and model quality. The goal of this metric is to impose a penalty on failing to achieve a target quality. VFLOPS is calculated according to the formula 1 and 2. The penalty coefficient is used to penalize or award the flops if the achieved quality is lower or greater than the target quality. Its definition is described as follows. As shown in Formula 2, achieved quality refers to the achieved quality in the evaluation. Target quality refers to the target quality defined in HPC AI 500 problem domain. The value of n is a positive integer, which is used to define the sensitivity to the model quality. The higher the number of n, the more loss of quality drop, as EWA has much more stringent quality requirement than that of image classification. We set n as 10 for EWA and 5 for image classification by default. Next, I will introduce the specification of HPC AI 500. First is the problem domain. First is the problem domain. Extreme weather analysis is a task to detect the pattern of extreme weather. Essentially, it's an object detection task. The application that wins Golden Bear Prize in SC18. And the second is image classification. As mentioned before, ResNet 50 and ImageNet is a de facto benchmark for optimizing HPC AI systems. And the data set, the extreme weather data set is made up of 26-year climate data. The data of every year is available as one HDF5 file. Each HDF5 file contains 2 data sets, image and boxes. The images data set has 1,000 example images with 16 channels. Each channel is a very high resolution image corresponding to 1 measurement per 25 square kilometers on Earth. The box dataset records the coordinates of the 4 kinds of extreme weather events in the corresponding images. And the dataset of image classification is ImageNet 2012 is a very famous dataset, and the Two adopted model is FastRCN and ResNet 50 version 1.5 respectively. Scalability is quite important in HPC AI application, and in this work, we use scaling ratio to depict the difficulty when scaling a workload from a single node to multiple nodes, which is the ratio. The scaling ratio is the ratio between computation and communication. The computation is a flop count needed in a one batch training, while the communication is determined by the model parameters. The scaling ratios of EWA and the image classification are 16.85 and 117.76 respectively, reflecting very different scaling characteristics. And these slides summarize the specification and the reference implementation of HPC AI500. And we use MPI and NCCL2 to implement the distributed training, and currently we provide the TensorFlow version. This is a visualization of EWA workload. The original climate image is processed to the labeled one. As you can see, the extreme weather pattern is bounded by the box. And next is the image classification. I think everyone must be familiar with this task, so I skip it without redundant introduction. Next, I'll introduce a case study using HPC AI500. This is our system configurations. We use our cluster has 64 NVIDIA V100, and the GPU memory is 32 gigabytes and is made by HBM, and the intra connection is NVLink, and the interconnection is Ethernet. And both EWA and image classification experiments are scaled out from 8 GPUs to 64 GPUs. In addition to the original FP32 version, we also evaluate the performance of the mixed precision and the model compression version, which are two frequently used optimizations in HPC AI applications. We take the 8 GPU experiments as a baseline. Our communication topology is a double binary tree, which is implemented by NCCL. We report the performance numbers of these experiments and perform follow-up analysis. For the FP32 precision implementation of image classification, the parallel efficiency is 0.91 and 0.85 and 0.71 on 16, 32, and 64 GPUs. For the mixed precision implementations, the parallel efficiency is slightly lower. They are 0.89, 0.82, and 0.67. There is a significant loss of parallel efficiency with the system when the system scale is 64 GPUs. The reason is that when the system scales up to 64 GPUs, more data need to be transmitted over the low-speed Ethernet and result in the parallel efficiency reduction. We also notice that communication compression doesn't improve the performance when the system scale is 32 GPUs or less. This is because that communication is not a bottleneck under this situation. However, when the scale is 64 GPUs, it contributes a lot. For the FP32 version, the performance improves from 345 to 414 TFLOPS. For the mixed version, the performance improves from 782 to 939 T-flops. The highest performance of image classification that we achieve is 939 T-flops. For the FP32 precision implementation of EWA, the parallel efficiency is 0.5, 0.37, and 0.36 at the system scale of 16, 32, and 64 GPUs. At the communication-intensive workload, communication compression of EWA achieves good results. When communication compression is used, the performance gain persists when the scale increases from 8 to 6, 32 and GPUs, and 64 GPUs, and the speed up is 1.2, 1.4, 1.6, and 1.5. The highest performance of EWA achieved through communication compression is 109 T-flops. Finally, we find why EWA and image classification have different parallel efficiencies. We found their different parallel efficiencies is due to distinct communication bandwidth consumption. As shown in the figure, we measure the communication bandwidth consumption of the FP32 precision implementations of EWA and image classification. EWA consumes a much higher communication bandwidth than that of image classification. It shows that EWA is a communication-intensive workload. In contrast, the image classification is a computation-intensive workload. Next, I'll introduce the ranking of HPC AI500 using VFLOPS. And we published the image classification, and it's a free level. It's a free level ranking based on our hierarchical benchmarking methodology. We published on our website on July 2, 2020. And it can, as you can see, and Fuji's achieves the 31.41 valid P-flops and finishes image classification in 1.2 minutes. The hardware consists of 2048 NVIDIA V100 GPUs, and they propose a novel communication algorithm by optimal scheduling group layers and implement a CUDA kernel that is dedicated to calculating norms in parallel. And we also provide auxiliary metrics such as training time, and quality. As you can see, although the Fuji, the training time is the shortest, but the model quality is not very good. It only achieves 75.1% in terms of top 1 accuracy. Finally, is the influence of HPC AI500 benchmark, and HPC AI500 has been listed as a key reference by Jack Donger, and these are 2 main websites of HPC AI500. Thanks. I'll finish my